Okay, welcome everybody to AP Physics. Today we are talking about work and energy and how everything is related here. We basically said yesterday that work was the change in energy. So depending on what kind of work. Now, we have this other word called mechanical. Okay, so when we're talking about mechanical energy, then we're talking about potential energies and kinetic energies. Okay, and so then non-mechanical would be, what do you think? Non-mechanical would be friction. Okay, or heat energy would be non-mechanical. Because heat is the summation of the individual particles' kinetic energies. So it's all the energy that a substance has according to the movement of its particles. So when you rub your hands together, you feel that heat, you feel it warming up. That's because you're turning your mechanical energy into non-mechanical energy, and you can feel that temperature increase. Well, temperature and heat are the same. Temperature is energy per particle. Heat is all of those energies per particle added together. Okay, so mechanical then is going to be a kinetic energy and potential energies. Non-mechanical will be friction and heat. And friction turns mechanical energy into heat. Okay, so when we're talking about this question here, and I think it's question 4 on the worksheet, number 1. And the question is, how much work is done in this situation? So we have a mu of 0.11. We have a velocity is constant. So if we're talking about velocity not changing, that means, and there's no change in height, that means that there's actually no change in the mechanical energy. And so you could say that the work that's done on this is not changed into mechanical energy, but then it has to be changed into what? It's going to have to be changed into heat. So if I'm asking you how much mechanical work is done on this system, it would be 0 because the velocity is constant. But if I'm asking how much work you're doing, that would be equal to the amount of work that is being done on the surfaces, increasing the heat. Okay, so what we want to figure out here is, well, we know that work here is defined as a force parallel to a displacement. So we know that our displacement here is 5 meters. Okay, so I'm just going to go up here with this work. So the work that you do has a displacement of 5 meters. And the parallel force to that would be, because you're pulling on this box at an angle of 30 degrees, this would be the part of the force that you're forcing on that box that is parallel to the displacement. Do you understand that? Okay, so that cosine 30, so it'd be cosine 30 t is how we could describe that. So then we could change our equation into work equals cosine 30 times t times 5, okay? That would be one definition of our work. But now we don't have tangent, so I'm not sure how good that's going to be for us. But at least we have that. What's the other thing that we have in play here is friction, right? Because we have a mu. And if this thing is going at a constant velocity, then whatever this cosine 30t is going to be equal to friction, right? So we can also label this cosine 30t then as the coefficient times the normal. Okay? So now there's another way to describe this. So we can also say that work is equal to the coefficient times the normal times 5, because the tension and the friction have to be equal to each other in order for there to be a constant velocity. Okay? So now we have to define this a little bit differently. So the work would be equal to the coefficient. The normal in this case would be 850, but is that what it actually is? No, because we're pulling up on this, so we have to subtract that part of tension out of the normal, because that's the amount less that the floor has to push up on that box. So it'd be 850 then minus sine 30 t. Okay, and that would be another definition of work. Okay, so now we can see we have two definitions for work. They both have t in them, so one way we could solve this problem is just solve for t. And then, once we solve for t, then we can plug it back into either one of these definitions, and then we should be able to have our work. So I'm going to set those two equal to each other. So cosine 30 times 5 times t equals mu times 850 minus mu times sine 30 t. Okay, so then in order to just solve for t, then you can just fill in your numbers at this point. Okay, and then you just go ahead and solve for t. So it's going to be 4.88 t equals 93.5. So t then equals, well, I guess I had a problem here because I forgot in this equation here, there still needs to be the 5 for that displacement. So this is the frictional force here, but I forgot about the displacement. So then our formula should look like this. And then we can see that the 5s actually cancel out. Okay, so 0.866 t then equals, so we have all our math back into the order that it should be. Sorry about that. So then when you just go ahead and solve for t, take 0.866 plus 0.055, and that'll equal 93.5. So T equals 101.5 newtons. Okay, so then we can put that into either one of our equations up here, and we can find out what our T, or what our work is. Okay, so we can either use this equation or we can use this equation, and we should be able to figure out our work on the system. Okay, so all this work then didn't add to mechanical energy, but it added to the heat. If we could measure the increase in the movement of the particles of the two surfaces, we should see that the increase in their energy is exactly equal to what we decided, or what we figured out here for work. Hopefully that explains some things for you.